So this is a summary of what we're going to be doing in today's set of notes. If we think about where we left off a couple of weeks ago, we'd start to talk about the Legendre equation. Of course, we converted theta into x. So we said that the x was equal to cosine theta. And it should be a theta rather than an a. That allowed us to come up with the Legendre polynomials. That's in table 6.3, page 283. We looked in that last class at orthogonality and normalization. We then recognized that we could go beyond the Legendre polynomials to these associated Legendre functions, and a summary of those associated Legendre functions is provided right here, and we've got this superscript in here that is not a power. It's just a way of describing the equation. We do have an exponent in here though, so this is an exponent or a power, and then we've got this differential, and then we find that there's the Legendre polynomial over here on the right hand side. When we solve this, when we solve the Schrodinger equation for the rigid rotor, we have already recognized that we need quantum numbers of m and j. Later on in this set of notes, we will consider m and l instead of m and j. We also, I've got it down here as well, we remember that x equals cosine theta. So at some point we've got to combine or convert back to theta. And so here's the function that we ended up with at the end of last class. So this is this y function, and it's made up really of the function that we came up with very early on in this chapter. We also have the associated Legendre functions, which gives us the theta term. And you'll note that all of the normalization constants are found in this section here that precedes the functions. You'll recall that the phi function in here did have a 1 over 2 pi value for the normalization function, but that finds its way into the overall normalization constant that's shown in here. And then last of all, in the last lesson, we talked about a simple convention where we have this I term in here at the beginning of the y function. So what will we do in this set of notes for today's class? We're going to recognize the full Schrodinger equation. So what we have here effectively is this h psi equals e psi type function that we've seen already, and this is really the solution to it, and we've got these the energies are a function of j, the quantum number j. We can also recognize that the Hamiltonian operator has been converted from Cartesian coordinates into spherical coordinates, and that's what's happening in here. So these are spherical coordinates. And what we're going to go on to consider is, since there's a relationship between angular momentum and the moment of inertia, we're going to recognize that when we consider the angular momentum operator squared, and that's in here, we end up with a very similar equation. And what this helps to tell us is that spherical harmonics end up being eigenfunctions of both the operator for angular momentum squared, and also an eigenfunction of an operator equation with the Hamiltonian operator. This tells us that these two measurables, if you will, commute. We're also going to go on and explore a little further from that. So we're going to learn that precise values of three components of angular momentum can't be measured simultaneously. That's this point in here. And we're also going to go on and think about how h bar is a fundamental measure of angular momentum, and that's here. So that's what we're going to look forward to over the next couple of PowerPoint sessions.